So for today's Do Now, there are two questions. Number one is actually one of the questions from yesterday's Do Now. It was the one that I saw the most questions on, so I just figured I'd put it on here again so we could talk through it. And then number two is a very common multiple choice question that I just made into a short answer question. And so we've seen a question like this before. For number one, a buffer is created using HClO and NaClO. So it tells us that it's a buffer. Remember that a buffer always needs to have a weak acid component and a weak base component. So if we know that it's a buffer, we can figure out what each part is. HClO starts with H, so it's an acid. So this is a weak acid. And then NaClO. So really we're focusing on ClO minus. HClO is a weak acid. ClO minus is its conjugate base. I'm ignoring Na plus because it's a spectator ion. So we have this buffer that's made of HClO and ClO minus. The pKa of HClO is 7.4. So this is the pKa. If the pH of the buffer is 8.4, what can you conclude about the concentrations of HClO and ClO minus in this buffer? So this is where we're comparing pH to pKa. Because when we compare the pH to the pKa of a buffer, that tells us what we have more of. If they're equal, we have equal amounts of both. But in this case, the pH is greater than the pKa. Think about what it means to have a higher pH. A higher pH means more basic. So if the pH is greater than the pKa, there's more base. And if we look at the buffer, the basic part is ClO minus. So I'll say the concentration of ClO minus is greater than the concentration of HClO. If the pH were less than the pKa, that means it would be more acidic, so there would be more acid. In number two, the table below shows the Ka values for 4 weak acids. Which weak acid, when combined in equimolar amounts, so that means equal moles, with its conjugate base, results in a buffer with a pH closest to 7.5. So remember when we make a buffer, the pH that we want to get to, we want an acid that has a pKa as close to that as possible. So we're looking for pKa closest to 7.5. Now, here's how we can actually do this without even using a calculator, because remember, on the AP test, we don't get calculators on the multiple choice. So we have to start looking at some shortcuts. It's not expected that you know how to take the negative log of something in your head. That's ridiculous. But you can estimate by looking at the exponent. If you take the negative log, so let's say that this was 1 times 10 to the negative 4th. If you take the negative log of 1 times 10 to the negative 4th, it's 4. So if you have a 1 in front, your negative log is actually the absolute value of the exponent. Well, we're just going to estimate. So is it going to be exactly 4? No. But if negative 4 is my exponent, I can say that my pKa is around 4. For HC3H5O2, this isn't a 1, but 1.3. All we can do to estimate is look at the absolute value of the exponent. So negative 5, that's a 5. So pKa is about 5. HClO, the pKa would be about 8. And then the last one, the pKa would be about 10. So to estimate taking a negative log, you can just take the absolute value of the exponent. And so then here are our approximate pKa values. The buffer that would have a pH closest to 7.5 would be the one that has a pKa closest to 7.5. And that's HClO. So our answer to this question is HClO. If we mixed HClO and ClO minus, we would have a pH closest to 7.5. The rest of these, this would have a pH around 4, a pH around 5, a pH around 10. So HClO would be the best answer for number 2. Any questions on the do now? Okay, if not, so you can get out your notes. We're actually going to be going through just 2 examples today. But before we get through the examples, I do want to review questions that I saw in the video, questions on titrations, solving for different variables in titrations, why should we worry about titrations, and then we're going to look at some titration curves, and we're going to use these particles again on the board to focus on what's happening in a titration curve. So these are just some important terms from the video. I was trying to put all of the questions that I saw onto one slide. So first, whenever we're talking about neutralizing, when I talk about neutralization, a neutralization reaction is when you add an acid and a base, and you create a salt and water. That's the definition of neutralization. It's a type of double replacement reaction where we add an acid and a base together. They neutralize each other by creating a salt and water. For a strong acid, strong base titration, we have something like HCl and NaOH. It produces a neutral salt and water. They're both neutral. That's why our pH is 7. When we talk about titrations, so the setup for a titration, hopefully we can get into the lab and do at least one titration, so you get to experience the joy of having to open one drop at a time. We have the titrant. That's what's in the burette. So the burette is a long glass tube, and we add something into the burette. We know the concentration of whatever we put in the burette. The analyte, it's just the sample that's down in the container, the flask or the beaker below. This is what we're analyzing. So why titrate? What's the importance? Well, titration is used to determine an unknown concentration. So a common example, there are 2 examples that I thought of right away. One of them is we can determine the amount of lead or of impurities in water. So like in Flint, Michigan, they have lead in their water. They actually titrated to figure out how much lead they have in the water. So they titrated with a concentration that they knew to figure out the concentration of what was in the container below. Another example, you can determine the purity of a medication. So chemists that are in the drug field, they can actually determine how pure a medication is, like aspirin, by titrating. So aspirin is acetylsalicylic acid. It's a weak acid. They can titrate with something like NaOH and figure out what concentration of acetylsalicylic acid they have in the aspirin. How pure is it? So it's used to determine concentrations. When we get into titrations, we talk about equivalence points and half equivalence points. So the equivalence point is the point where all of the acid or the base, whatever is in the container underneath, all of the acid has been neutralized. So that means that you've added enough base into the acid that it's completely neutralized. The most important thing about the equivalence point is that the moles of the titrant, so let's say the moles of base, equals the moles of acid. A lot of times it's called the stoichiometric equivalence point because we use the mole ratios. So we can say we have 1 mole of HCl to 1 mole of NaOH, and we can use that to help us find molarity. Half equivalence point. So this is important where we're looking at weak acids or weak bases. The half equivalence point is the point where half of the acid or base has been neutralized. So when we have a weak acid in this container, the half equivalence point is when half of this weak acid has been neutralized. The importance of the half equivalence point is that the half equivalence point is half the volume of the equivalence point, not half the pH, but half the volume. The pH at the half equivalence point is equal to pKa. That's one of the most important things about half equivalence point. pH equals pKa. If it's a weak base, POH equals pKb. Also at the half equivalence point, moles of acid is equal to moles of conjugate base. And what we'll do is we'll look at a titration curve and we'll look at what we have in the beaker at every point in the titration curve. So if we start by looking at a strong acid, strong base titration, and you labeled different parts of a titration curve in your notes, but this is a strong acid, strong base titration. I'm going to show you how I know. I look at 3 places when I'm given a titration curve. I start by looking at the initial pH. I notice here that the initial pH is very low, maybe 1. That tells me right away, well, that's probably a strong acid. I look at the ending pH. So up here, the pH is pretty much 14. A very high pH tells me it's probably a strong base. And then I can also look at the pH at the equivalence point. So the equivalence point is halfway up kind of the straight line. This is the equivalence point. At the equivalence point, the moles of acid equals the moles of base. And then anywhere else on this curve, if we need to find pH, strong titrations are stoichiometry. So kind of like, was it last Friday when we were looking at acid-base neutralization? When it was a strong reaction, it was just stoichiometry. All this titration curve is showing a strong acid, strong base reaction. It's always stoichiometry. So you'll notice that the pH before the equivalence point is due to excess acid. So it becomes a stoichiometry or limiting reactant problem. Anything after the equivalence point, you have extra base. So if we think about what this looks at the particle level, let's do this. So let's say I have HCl. So here's HCl. Now this isn't actually what it looks like when it's in the beaker, because it's a strong acid. So H plus and Cl minus will actually dissociate. So before any base is added, we're at this initial point. If I add 1 NaOH, right, so here's NaOH. NaOH is a strong base. So as soon as I put it into the container, it's going to break apart. It's going to dissociate. Na plus is a spectator, it's just floating around. As soon as this OH minus gets into the beaker, the H plus from the acid neutralizes that OH minus. So I'm somewhere down here still. So I'm somewhere down here on the titration curve because I still have acid. So Cl minus is a spectator, Na plus is a spectator. They just float around in here. What I'm focused on is the H plus and the OH minus. I add another OH, right, as soon as it gets into the beaker. Technically I add an Na plus. But as soon as the OH minus gets into the beaker, another H plus reacts to neutralize it. Makes water. Once I add this third hydroxide, notice now all of the H plus has been neutralized. At this point, I have Na plus, Cl minus, and H2O. when all of the acid has been neutralized, right? The moles of acid equals the moles of base. We are at the equivalence point. The equivalence point of a strong titration is 7. Na plus is neutral, doesn't affect the pH. Cl minus is neutral, it doesn't affect the pH. Water is a neutral solution. So nothing affects the pH here, so it's a pH of 7. But if I add one more OH minus, there is nothing to neutralize that OH minus. So as soon as I add one more OH minus, now I'm all the way up here. That's why the pH jumps so much. If you're in the lab and you're doing this jump from the equivalence point to here is 1 drop. I had somebody last year that had to titrate 3 times because they added 2 drops instead of 1, and they went from here all the way up to here in 2 drops of NaOH. Because there's nothing else to neutralize. So as soon as you add a hydroxide, now you have excess base, and the pH is really high. So that's looking at a strong titration. Again, it's all stoichiometry. Tomorrow, we're going to focus on these strong, weak titrations. So if we take a look at this titration curve, this looks a little bit different. If you look at the strong curve, notice how it's a really nice S shape. Pretty flat, shoots straight up, pretty flat. A weak, strong titration looks a little different. It has this extra little curve in it because this is where we form a buffer. So the pH is resistant, or the solution is resistant to changes in pH. When I'm looking at a curve like this and I'm trying to figure out what it is, I start by looking at the initial pH. I say 2, so it could be strong or weak. So I go and I look at other points. Up here, I'm ending at a really high pH, so that tells me that it's a strong base. Then I look at the pH at the equivalence point, and I notice that it's not 7. The only titration curve that has a pH of 7 at the equivalence point is strong. This has a pH above 7. So that tells me if this is a strong base, I'm starting with a weak acid. Now this is where they always like asking questions about what you have in the container. So if I do acetic acid, right, so here I have acetic acid in the beaker. So this would be my initial. All I have in the beaker right here, before I add any NaOH, the only thing I have is acetic acid. It's a weak acid. I can figure out the pH using an ice table like we did in the last chapter. As soon as I add 1 hydroxide, I'm going to keep Na plus out just to save some space. Just remember, Na plus would be floating around in here. I add 1 hydroxide. Well, a neutralization is an acid plus a base. So 1 acetic acid is going to neutralize. So I have H2O and acetate. I do it again. I have H2O and another acetate. At this point, notice how I have 2 acetate ions and 2 acetic acid molecules. After the first NaOH addition, I was right here. I still had more acid than base. At this point, my acid and my conjugate base are equal. My acid and conjugate base are equal. This is the half equivalence point. The half equivalence point is where pH equals pKa. This is the half equivalence point. Notice the equivalence point happens at a certain volume. When I divide that by 2 at that volume, that's the half equivalence point. Then I can add another OH minus, and the neutralization reaction will keep going until finally I get to this point. I have acetate and water. My acid has been completely neutralized. There's no acid left. This is the equivalence point. This is where moles of acid equals moles of base. which also equals the moles of salt that was formed. The pH in this container now is based on the acetate ion. The acetate ion is a weak base. That's actually why the pH is above 7, because acetate is a base. So when acetate undergoes hydrolysis, it creates OH minus. And then as soon as I add another hydroxide, now my pH has spiked way up here. Tomorrow we'll focus on calculations with strong, weak titrations like this, because this involves equilibrium. Today is just stoichiometry. Tomorrow we'll look at equilibrium. Now I just want to show you what this looks like, because this looks a little different. It goes the other way. Well, here I'm starting with a base, and then it goes down, all the way down over here. So because it has this little extra curve in here, that tells me that I'm dealing with something that's weak. So this is actually showing a weak base, strong acid calculation, or titration. So the pH is ending at about 1, strong acid, starting at about 12. I know it's a weak base because of this extra curve. Notice that the equivalence point is below 7. So the pH at the equivalence point is acidic because of that conjugate acid. So the only difference between a weak acid and a weak base titration is where you start. It still curves down, right? Half equivalence point for a weak base, POH equals PKB, because it's a base. And then you keep going all the way down the titration curve. So we're going to take a look at example 9. We're going to do 9 and 10. 15 is a multiple choice question. We'll do that just really quick, so it won't take long. And then you're going to have time to work on mastering. So if in your notes you flip to example 9, 9 and 10 are just stoichiometry, right? No ice tables, nothing like that, just stoich. So if you actually think back to, oh man, this was chapter 4, part of the summer work, solution stoichiometry. That's what we're looking at in these 2 examples. So this says how many milliliters of a 0.085 molar NaOH solution is required to titrate 40 milliliters of 0.09 molar HNO3. So let's start by labeling the solutions. NaOH, OH tells me it's a base. Na plus is part of the lowercase b, so it's a strong base. HNO3 is one of the 7 strong acids. Strong, strong tells me it's stoichiometry. Strong acid, strong base, reaction is just stoichiometry. No equilibrium, just stoich. So if we write our balanced equation, just to make sure that our mole ratio, we know our mole ratio, NaOH plus HNO3. This is an acid-base reaction. It's a neutralization reaction. Acid plus base yields salt plus water. So our positive ions switch places. That gives us H2O and NaNO3. Na is +1, NO3 is -1. So there's our equation. And if I take a look, it's already balanced. The reason this is important is because this tells me that for every 1 mole of NaOH, we need 1 mole of HNO3. So they tell me that I have 0.085 molar NaOH, and I'm trying to figure out how many milliliters. When I have 0.09 molar HNO3, and I have 40 milliliters of that. So here's really what we're trying to do. Is we want to go to moles of HNO3, use stoichiometry to go to moles of NaOH, and then go back up to NaOH. So this is just stoichiometry. Take the information of HNO3, go to moles, use the mole ratio to go to moles of NaOH, use the molarity to get liters. Here's another way you can think about titrate, because I had some people ask, what does it mean when it says required to titrate? Think about it saying required to react with. That's all titrating is. It's a reaction. So I'm going to start by taking my molarity and my volume and figuring out moles. So 0.0900 molar HNO3 is moles over liters. Be careful when you use molarity. Has to be liters. 40 milliliters is 0.04 liters. Remember, there's 1,000 milliliters in a liter. So I'm starting by figuring out how many moles of HNO3 do we have in this reaction. We have 0.0036 moles, and this is HNO3. Make sure you're labeling everything as well. Now this is where my mole ratio comes in. Once I have moles of HNO3, I can figure out NaOH from the mole ratio. For every 1 mole of HNO3, we need 1 mole of NaOH. I know it's a 1-to-1 mole ratio. But there was a question like this on the AP test a couple of years ago with the free response, and you had to show this to get one of the 2 points. So even if you just write a note that says, 1-to-1 acid to base ratio, you had to show this somehow to get the 1 point. That means that we have 0.0036 moles of NaOH. And then we want to go to milliliters. So now we have molarity of NaOH, and we need to get back to volume. So I have 0.0850 molar NaOH. It's 0.0036 moles. Remember that this is over X liters, not milliliters, but liters. When you solve, multiply by X, divide by 0.085. When you do that, you get 0.0424 liters of NaOH. It asks for milliliters, so you multiply by 1,000. Remove the decimal place over 3 times. 1, 2, 3. .42 milliliters. So what this was is when you're titrating, when it's reacting, you have equal number of moles. So it's just stoichiometry. Take your information, go to moles, use the mole ratio to go to moles of the other substance, and then go back to volume. Now, could you do this as one big, long problem? Yes, you could, using molarity as a conversion factor. And then you would get the same thing. Questions? Questions on example 9. So let's look at example 10. This is another stoichiometry problem. So start by reading through the question and labeling. Label the substances, because if it's a strong titration, it's nothing more than a stoichiometry problem. So it says that you have HNO3 and KOH. So HNO3 we labeled in the last problem. HNO3 is a strong acid. OH minus is a base. And then K plus is part of the lowercase b on the periodic table. So we have a strong acid and a strong base. Strong acid, strong base means stoichiometry. Start by writing the balanced equation just to make sure our mole ratio is what we think it is. A neutralization reaction, an acid-base reaction, whether it's weak or strong, an acid-base neutralization reaction is a double replacement reaction. So KNO3, because K plus is going to combine with NO3 minus, plus H2O. And that's actually balanced. So we have a 1-to-1 ratio. So this is telling me I have 100 milliliters of HNO3. I have 45 milliliters of a 0.025 molar KOH solution. I want to know the molarity of HNO3. So because this is a strong titration, we can figure out our moles of KOH, use that to find moles of HNO3, and then use moles and volume to find molarity. So I'm going to start by using all of the information of the known substance. I have a known volume and known molarity of KOH. So 0.025 molar KOH. Molarity is moles over liters. Molarity is always moles over liters. 45 milliliters is 0.045 liters. Because again, remember there are 1,000 milliliters in 1 liter. So we can start by figuring out how many moles, 0.001125 moles of KOH. And it's a 1-to-1 ratio. So for every 1 mole of KOH, we need 1 mole of HNO3, which means after this reaction, we have the same number of moles of HNO3. So again, it's stoichiometry. Take your information and go to moles of a given substance, find moles of the other substance, and then go back out to whatever unit that you need. In this case, I'm trying to get molarity. Molarity of HNO3 is moles over liters. So 0.001125 moles over, not 100 liters, but 0.1 liters. Molarity has to be in liters. So that's 0.01125 molar HNO3. .01125 molar HNO3. So strong acid, strong base is nothing more than stoichiometry. Right, just a stoichiometry problem. Questions on this before we look at just the multiple choice? If not, go ahead and flip to example 15. All right, example 15, and the reason I want to look at this is because this is just a multiple choice question that we can look through, and it helps look at titration curves and what we have in the container at different points of the titration curve. So this multiple choice question says, at which data point is the molarity of acid greater than the molarity of the conjugate base? So this is a weak, strong titration. Here's how I know it's weak. Look at the pH. Starting at a pH of 5. That's not a strong acid. That's a weak acid. Ending at a pH of about 13, so that tells me it's a strong base. Plus the equivalence point. The equivalence point about halfway up the spike in pH. The equivalence point is significantly above 7. So that tells us it's a weak acid, strong base titration. Now we're trying to figure out where is the acid greater than the conjugate base. So I know at point T, this is the equivalence point. At the equivalence point, moles of acid equals moles of base. And all acid and base is neutralized. So the acid is gone. At point T, the acid is gone. At point T, it's like this in the container. Water and conjugate base. Point R, this is the half equivalence point. The half equivalence point is where acid equals conjugate base. The importance of the half equivalence point is where the acid is equal to the conjugate base. Point S, we have more conjugate base than acid. So that would be like this. This would represent point S. We have more conjugate base than weak acid. At point R, at the half equivalence point, it looks like this. Equal acid with base. The only point that we have more acid is point Q. And then a quick question here, what's the pKa? Remember, you can figure out the pKa using the half equivalence point. The half equivalence point, pH, equals pKa. So the pH here is about 8. pKa is about 8. This period, you now just have time to work. And what I did is I went through during first period and I started looking at what questions, examples, practice that we've done matches up to what mastering numbers. And so I put this table, this is not all of them because we haven't really gotten into more titration questions yet, but this gives you a good idea. I mean, essentially 1 through 14, you have a lot of them that match up. I did go through this morning with somebody in first period and I was working through number 10 with her. And so I have 10B and 10C up here on the board. So if you want to just do number 10. Number 10 is very close to number 7, like example 7 that we did. But B and C, I have the answers up here. Number 20 did not have an example that matched up with it, but I just wanted to give you a little hint for number 20. You can use stoic for part A, determine the limiting reactant. pH depends on what you have left over. And then the last thing is the last video that deals with titration. So in Edpuzzle and Google Classroom, you have video 8.4. It's like 8 minutes. So much shorter than the other ones from yesterday. I know they were long. I apologize. There's just a lot of information in titrations. And so 8.4, this is the last video until next Wednesday. So this will be the last one. No video over the weekend, anything like that. So if you would rather watch the video now, you can. Or if you want to use this time to work on mastering in groups, you can grab a marker, work on mastering as well. But I'll leave this up here. So you can use this. Look at number 10 if needed as well.